Usual. Yeah. Um, on Sunday we talked about new concept of sequences of functions. Yes, we talked about sequences of functions, what we called pointwise convergence. Let's remind it. Um, let fn be a sequence of functions defined in some segment I. It can be all of R, it can be 0 to infinite, it can be 0 to 1, etc., etc. So don't write it down as a closed interval, but just I. Um, we say that Fn converges converge to F in meaning of pointwise and denote Fn goes to F if for every x in I we have that the limit of the sequence of numbers f and x is the number fx. We consider x to be a constant or a parameter or something like that. When we find the limit, f is called the limit function or the function of limit, whatever. For example, we saw that, still a reminder, example, f and x, which is x to the power of n, in the segment 0 to 1, the limit function is is 1. It is 1 when x is 1, because 1 to the power of n is just 1. Really, converges to 1. But for every other x in our segment, half to the power of n, third to the power of n, stuff like that, when the base is smaller than 1, the power tends to 0. And again, these little lines are the least technical way to space between the numbers. So as far as I can remember, we totally talked about something like 10 examples on Sunday. 8 of them just examples with different kinds of functions and different behaviors. And then we ask ourselves 3 or 4 questions. If Fn are all continuous, does it mean that F is continuous? If Fn are all differentiable, if Fn are all integrable, blah, blah, blah. And all the answers were no, 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 and no. So what are we going to do today? We're going to define a different, stronger notion of convergence, which is called uniform convergence. And then we talk about it, how do we actually find it, some equivalent conditions to this uniform convergence. What does it mean, geometrically speaking? And then we can ask ourselves the same questions we asked on Sunday, but today some of the answers, not all of them, but some of the answers are going to be yes, not just no, no, no. So this is our main um, notion today, the uniform convergence. Before I define what uniform convergence is, I want to write down what pointwise convergence means explicitly. using the definition of limit of sequence as we know it from Infi1. Um, First of all, we write down what pointwise convergence means explicitly, rather than explicitly, using the definition of limit, of a limit. As a, what is it? Point convergence. Let
Find it by.
be some element in I. Then for every who definition of limit, every epsilon, positive epsilon. This is the middle of our course. We have, let's say, 36 lectures.
What did we say I meant?
What?
What did we say I meant?
Segment. 0 to 1, all of R, 0 to infinity, 2 to 5, a segment. As I mentioned, I don't want to write it down as AB because it's not just about closed segment. It can be an open one, an open interval, infinite interval, in fact. So I started to say, yes, course in calculus. We got to the middle of the course. Yeah, I think 26 lectures. This is the default. We we missed one in the first week, and we're going to miss one on Sunday. Not this Sunday, next Sunday. It's Hanukkah, and Tuesday after this Sunday. Not that it's going to be a Sabbath event. So maybe we're going to have 25 total, but 26 is the default. So, as of the course, the first time we saw epsilon, it's about time. Wherever epsilon greater than fs greater than 0, there is, I don't know, some an epsilon. That's how I denote it. Maybe Aries denoted it with big N, capital N, or N0, or something like that. There is an N epsilon such that for every N which is greater than epsilon, an epsilon, we have that the distance between f and x and fx is smaller than epsilon. This is the definition of limit, which you saw, lecture number 3 or 4 in Infi1. It's not an goes to L, it's f and x goes to fx. But besides, it's all the same. We start here with x in the background. I mean, let x be an I, and for this x, we have a sequence of numbers that is convergent. It converges to fx, and we wrote down the definition of limit explicitly for this case. Now, how do I define uniform convergence? So we can see what is the difference between both of the definitions clearly. Now, let Fn be a sequence of functions converging pointwise, meaning converging to a function f in some segment I. We say that the sequence Fn is uniformly convergent. That's the definition. That's all the up. to F. And I want to say that one can define this convergence without explicitly referring to the function f, but the way I show things, it's better that way. We have a function f already, f and the sequence converges to it in the pointwise meaning. And now we know that it can be uniformly convergent. How? Convergent to f, and we denote with double arrow. How do I write it? Right arrow. Yeah, right arrow. Two arrows. Um, if for every epsilon, let's write down explicitly, var epsilon greater than zero, there is a natural number n such that for every n greater than an epsilon and for every x in the segment, we have that the difference between Fn and Fx is smaller than epsilon. What is the difference between these two definitions? Where do we put the for every x? In the pointwise definition, we look at every x, and then when x is a constant, is given to us, therefore epsilon, blah, blah, blah. Here, in the uniform convergence, we need these n epsilon to work for every and for every x. I mean, this level, this index in the sequence should work for every x in the segment uniformly. This is why we call it uniform convergence. Geometrically speaking, and let's write down the difference in this, the difference. Um, we want the same n epsilon, and the same n epsilon to work for every x, and not for every x having the same epsilon. We know that changing the changing the places of the quantifiers in the sentence changes the sentence. This one is a stronger one. Not just that, every x has its own n epsilon, blah, blah, blah. There is an epsilon that works for every x. Geometrically speaking, when Fn, right arrows to F, it's uniformly convergent to F, there is um, for every epsilon, positive of course, epsilon greater than zero, there is an epsilon, some index in the series, in the sequence, such that all the functions of the sequence after the index and epsilon um, after this index are in an what I called epsilon strip way. strip around F. I want to draw it. For example, I don't, it doesn't necessarily write down the function, especially just the graph. This is the x-axis, it's enough on to y1. Let's say that this is the function f. Now, what do we say here? That for every x, there is a level n epsilon and index in the sequence n epsilon such that after n epsilon, f and x and fx, the distance between them is smaller than epsilon for every x along the segment. So we have what I called an epsilon strip or something like that. In Hebrew, I call it epsilon stripe, pas epsilon, but strip. That's what epsilon. It's better. Um, Imagine that they are the same uh, lines, and here the distance is epsilon from here to here. So what do we say? We say that such level as an epsilon exists and next in the sequence. After that index, all the functions fn are inside this epsilon strip. All these brown red ones are fn. And needed to be shown, geometrically intuitively speaking, is an example of functions where this is not happening. Yeah, so we can compare them and have better understanding of what the hell is happening. What do you want to do? I want to move it down a little bit so I can copy and paste it without copying some of the letters as well. The text, I mean. Listen up. And now. Winky shift S. Mm-hmm. Scaling. Okay. Um, on the other hand, we look at an example in which this is not happening, meaning that the convergence is not uniform. But formally speaking, we, of course, do not use drawings. We will state today some equivalent conditions to these not very nice epsilon thing, and we use them to formally prove or disprove that sequence of functions is uniformly convergent. But let's look at an example. I think it's for the better. Let's say f and x to be x to the power of n, our known example. And to make it simpler, let's look at the segment between 0 and 1 without 1. Here, as we know, the limit function is just 0. I mean, when 1 is included, then x 1 to the power of n converges to 1, and the function is a piecewise function. But when we give up, we fire 1 from a segment, then the function is always 0. And now, and this is the drawing we have already drawn, let's just say, drawn already, whatever. In Sunday, you get the following problem. Let's use the black one. I run down the x-axis up here. up in here, up in there. And this is the y-axis to have some proportions. Of course, we do not have them exactly. How does the limit function looks? It's the x-axis. This is f. It's only 0. How do the fn look? We have the first function is fx is x, f1x is x. The point here is 1, 1. Yeah, it's not proportional, so I always say. And here, the second function is x squared, which is something like that. The third one is x cubed. That's some wider belly, I want to call it. These are fn. Now, if you look at f, it's only the x-axis, and you surround f with an epsilon strip with width, you say it, of let's say half. Epsilon is half. At some point, every function just burst out of the epsilon strip. I mean, here it's even worse than what I need from a counterexample. I mean, it is uniformly convergent when from starting from some level, from some index, all the functions are inside the strip. So what is the opposite? There is some function that goes out. Here, all the function goes burst out from the strip. So intuitively, geometrically speaking, here the convergence is not uniform convergence. It's pointwise, but not uniform.
I mean, I know this is true. I mean, does it have to be true for every point on the domain?
For every point, for every epsilon. What changes? The level. Where do we start to get the functions inside the strip? Of course, when the strip is thinner, you need to look at higher indexes in order to get the functions inside the strip.
In this case, the function have infinity, right?
The f,
Yeah.
it, it is pointwise converging. It has a limit for every x, a finite one. But for every x, epsilon needs a different index and epsilon in order to maintain the convergence. You can use the same level for every x along the segment. Let's copy and paste it as well.
Can I ask a question?
Yeah, just let me paste it again so we can look at it.
In this example, why did you use x squared and x cubed if n is between 0 and 1?
No, 0, 1 is the domain of x. N is a natural number.
Oh,
It's the index
right,
of
okay.
the sequence here. Let's say it's 9. It's 9 is good. Okay. So, geometrically speaking, this is what uniform convergence says. Now, how do we actually, with a given sequence of functions, check if the sequence is uniformly convergent or not? Of course, we don't have to draw things and look for the epsilon strips, but it's nice to have this geometric point of view. We use the following theorem. The following condition, the following are equivalent. Equivalent. First of all, Fn uniformly convergent to F in the segment I, meaning that for every epsilon, blah, blah, blah. And the second condition is dn tends to 0. The sequence dn tends to 0. Okay, nice annotation. What is dn? Where dn is the supremum in the segment of f and x minus fx. One can write down two more equivalent conditions. We know from infi1 that every limit, every convergence of a sequence, we can write down by definition. We can use sequences in order to define the limit of a function, and we can write it with the Cauchy criterion, using n and m for epsilon. I'm not going to use it here. I don't think we need to use it here. So I'm not going to write it down. But if you look those notes from previous semesters or in the morning, 8 a.m. in the Hebrew lecture, I did mention it, but it's not necessary. It's not important. What I want to do is two examples. One where the sequence is uniformly convergent and one where it is not. It's if and only if it's equivalent conditions. Then I want to prove this theorem. It will be easy, don't be afraid. And then we can, as I mentioned, ask our questions. If Fn continuous is F continuous, blah, 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 when we talk about uniform convergence and not just about the pointwise convergence. So examples, one that is and one that is not. Examples. Let's start with the following sequence. Something similar to what we saw on Sunday. Sinus. We decided that we prefer sinus, yeah, instead of cosinus. Treacherous cosinus. You derive it and you get the minus. Sinus. Let's say number you like. Okay, I choose 7. Next, above, let's say 13n. In all of R. So, as I mentioned, as I defined it, we first of all need to find the limit function f in the pointwise convergence. Meaning, and then check if this dn, whatever it is, tends to 0, yay or nay. So, first of all, the limit function is fx is the limit of n when we consider x to be a constant, and here this is fn. Now, what is the limit here? We consider x to be a constant?
0.
0. Yes, sinus is bounded. The denominator goes to infinity. So we know that this is 0. One can write it down as, I don't know, 1 above 13n multiplied by sinus, and it is 0. Function that goes to 0, I call it in Hebrew afisa, a zeroing function, multiplied by a bounded one, it still goes to 0. And now we can look at the dn. This dn is the supremum of the difference between f and x and f, and the condition of dn goes to 0 is made up of two steps, just like the improper integrals. It doesn't have, not connected to improper integrals, but the definition is similar. What do I mean? When we define the improper integrals, we define it by two steps. You calculate the integral, and then you take the b or whatever letter we choose to 0. It's the same here. We calculate or doing something else that we already we'll see already soon. See, calculate the dn, and then we ask ourselves, okay, this dn we find, does it go to 0? Yes or no? So here we talk about the supremum of the functions. We can use the nice absolute value parentheses. Minus 0 and minus 0 we don't need to write, and 13n is always positive, so it's actually an absolute value only on the numerator. And now, on one hand, we can find explicitly what dn is. We know that sinus is bounded by 1, and there are values of x of which the sinus is 1. X is pi above 2 above 7n, which gives us exactly sinus of pi above 2, half a pi, which is 1. But on the other hand, what do we need to know is not necessarily what dn explicitly is, just if dn goes to 0, yes or no. So even if we don't find dn here exactly, because we know that the sinus is bounded by 1, we have our our sequence dn bounded by 1 above 13n, which tends to 0. So by sandwich, and one can ask yourself, okay, where's the second bread? Slice of bread of the sandwich. When dn is smaller than something that goes to 0, why is it greater than something that goes to 0? Take note that dn is always non-negative. It's supremum of something in absolute value. So you always have 0 on your left side. If you want to show that dn goes to 0 by sandwich, you only need to find something bigger that goes to 0 as well. By sandwich, we have dn goes to 0, and so fn converges uniformly to f in R, the real numbers. What else? I have something else to say. Observe that here, when considering or calculating or finding or whatever the supremum, the variable is x, and we consider n to be a constant. After we find the supremum, we have some expression dependent on n, and then we say, okay, let's take n to infinity. Does dn go to 0? Yes or no? So here we start to play this sometimes gentle game. When we see it more clearly, more explicitly, probably in the second example. But let's say note we sometimes don't need to find dn explicitly. We need to know if dn goes to infinity or no, or not. And sometimes sandwich or other considerations is enough. This is my first note. The second one, when we calculate the supremum, x is the variable, and we consider n to be a constant. So who is the constant? Who is the variable? It depends. What question we need to answer? Calculating the pointwise limit, we consider x to be a constant. Let x be whatever, and we take n to infinity. Finding the supremum, we consider n to be a constant. And for every x in the segment, what is the greatest value f and x minus fx can achieve? Okay. Two notes, and then we can move on to the second example. Any questions about the first examples? And we noted notingly after we did it.
Yeah, but
Yeah.
can you just go over why dn is bigger than 0?
What?
Can you explain why dn, we said at the beginning that dn is bigger than 0?
Dn is the supremum. Intuitively, it's the maximum. Formally, we know that sometimes there is difference between the supremum and the maximum of the difference between f and x and fx. And by my theorem that I want to prove after we finish with the examples, it is equivalent to the uniform convergence, that dn goes
No,
to 0.
I understand all of that. Just why at the beginning did you start off with 0 being smaller than or equal to dn? Like, why did we say that?
Why need it to be the limit to be 0 and not something else?
No, no, no. You said
Yeah.
it says now we have 0 smaller than d of n is equal to blah 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 blah. Why is 0 smaller than d of n?
Because dn by definition is the supremum of something in absolute value, and absolute value is always greater than 0.
Right. Okay. Cool.
Any other questions? So for my second example, we look at an example similar to the basic one of x to the power of n, but a bit different. X to the power of n minus x to the power of 2n. And we look at it and the segment between 0 and 1. A spoiler, it's not going to be a uniformly convergent sequence. I want the example of something that is, or the example of something that is not. First of all, we find the limit function. There are some joyful people outside.
Yeah, well,
Yeah, they do not study computer science. We, oh,
the royal.
more precisely, you are going to be joyful afterwards.
I don't think there are enough stacks. Yeah.
I mean, the infinity number of stacks can be divided to 2 or 3 or whatever infinities you need. We find the limit function. Fx is the limit where n goes to infinity of f and x, and it is the limit of xn to minus x to the power of 2n. And now, when x is smaller than 1, and yet again in the segment from 0 to 1, we have both of xn and x2n goes to 0. 0 minus 0 is 0. If, on the other hand, x is 1, we have both of xn and x2n goes to 1. The bottom line, it's still the same, it's still 0. So this way or that way, we get 0, so one can say fx is 0 for every x in our segment. In this example, the previous one, we both have a limit function 0. We know that it's not necessarily always happening. We, as I mentioned, saw something like 10 or 11 examples on Sunday. Most of them, the limit function was not 0. Now, we can move to the dn. And as I said in the first example, because dn is always greater than 0, if you try to find to show that it goes to 0 with sandwich, just find something greater that goes to 0 and you're good. Fn x minus fx. Here it is xn minus x2n minus 0. And here we can do two little things before we continue. First of all, minus 0, we don't have to write it down. Secondly, when we talk about x's between, when we talk about x's between 0 and 1, x to the power of n is larger than x to the power of 2n. For example, if you take, oh no, half, okay? Half to the power of 3 is larger than half to the power of 6. The greater the power, the smaller the greater the one above, the smaller the expression is. So xn minus x2n is a positive, or at least non-negative expression. We can say goodbye to our little friend, the absolute value. And now, unlike the first example, it's not so simple to say, okay, it's always smaller than blah, blah, blah. It's not. I mean, if we take if we take bigger and bigger x's, where x to the power of n is bigger and bigger, then the x to the power of 2n gets bigger as well. And I don't know to say something which is surely true about the subtraction. And if we take smaller x's, it's all the same. We need to do something else here. And what is the something else? Something that's common when it comes to these type of questions. We have a function that is continuous. It's differentiable, anytime you want, but it is continuous. So by Weierstrass theorem from Inphi 1, we know that a supremum is not just supremum. It's actually a maximum. There is some point x along the segment that when we put it in the function xm minus x2n, gives us the maximum value of the function. Let's write it down. The function xn minus x to the power of n is continuous. So by, may Allah forgive me, I don't have to write Weierstrass in there. I'll ask the Weierstrass. I was almost right. It's E-I-E before the R. I remember the double S. No, I'm by definition, I'm Austrischer myself. You have Austrischer citizenship. My great grandfathers ran away, 38 or something like that. So they were fair enough to give us the citizenship back. But I never used it. I always travel with I don't travel so much when I travel, just the Israeli passport. I please need to use it from time to time. So by Weierstrass, um, we know that f has a maximal value, maximum. We can write instead of the soup, we can write max. Okay, so First look is just no, cosmetic fixation. Instead of soup, you wrote it's max. Okay. So what? It's an important difference. When it comes to maximum, we know basically from high school, but I'll remind it here right now, how to find it. How do we find? And we know how to find, or at least how to look for, finding something else, how to find um, extrema, not just maximum, extrema of such functions. How do we do it? Firstly, we find, in Hebrew we call it נקודות חשודות, the suspects points. We find the points that we suspect to be the maximum, which point, first of all, points where the derivative is 0. The endpoints of the segment are always expected to be extrema when we look at the closed segment. And thirdly, what probably didn't happen in high school, points where the derivative is not defined. I mean, absolute value in its spitz down there or something like that. It can happen here. We're not children anymore. Points where the function is not differentiable, meaning that there isn't no derivative there. And then when we collected, after we collected all the, gotta catch them all, yeah, all the suspected points, we find the values of the function, find the value without the s of the function in every point, semicolon, the point with the greatest value gives us the maximum, and it's more importanter, the maximum, the greatest value is the maximum. And the greatest value, that's what you look for on the first place, is the maximum. So all this paragraph, starting with the firstly, isn't necessarily connected to uniform convergence or sequence of functions. It is a known technical process. How do we find the extrema of a continuous function? And usually it's differentiable, like we are used to from school, and finding the extrema, maximum, and minimum. In the last part of our course, when we will talk about, when we discuss functions of more than one variable, we will get back to this. How do we find the maximum of function on some domain when it has more than one variable? And we will discuss it again. Right now, it's enough to write down this process here in light blue. Let's see how it goes in our example, and then you can ask your questions. In our example, the function is always is differentiable everywhere. Nice. We don't have points where the function is differentiable. We need to solve derivative equals 0 in order to find some suspected points. So 0 is the derivative of the function. Here it is fn because f was 0. But generally speaking, it's the absolute value of the difference between f and x and fx, which is not necessarily equal fn, only if f is 0. So I don't want to write fn instead of it. Don't get confused. I want to call it g if you want some letter or something else. Let's find the derivative. As I mentioned, we consider n to be a constant and x to be the variable. So I derive it, differentiate it that way. Now we need to solve it when it's actually 0. We can take out n, x to the power of n minus 1 as a common expression, and we are left with 1 minus 2x to the power of n. Correct me if I am wrong. And we have two options here. So n x n minus 1. Oh, more or less. N x n minus 1 is 0, meaning that x is 0. And 1 minus 2 x to the power of n is 0, meaning that x power of n is half, which means that x is the nth root of half. So we find two suspected points, and it's totally fine that it is dependent on n. As I mentioned here, we consider n to be a constant. What about the endpoints? The endpoints are 0 and 1, and we have a total number of 3 suspected points. 0, 1, and the square root, the nth root, excuse me, of half is suspected points. This is the first and the main step of the process of finding the maximum of a continuous function in a closed segment. Second one is just calculating the values of the function in these suspected points. And observes what is the greatest one. Let's put some spaces, be easier to read afterwards. Now, calculating the values of f n x minus fx in the suspected points gives us let's see. The function is x to the power of n minus x to the power of 2n. Okay. If we plug in 0, we have 0. If we put 1, we have 0 again. So 0 and 1 are the minima points. And for this nth root of half, we get something more interesting. By the rules of powers and by the gods, we get half minus half squared, which is quarter. So 0, 0 quarter, the maximal value. Maximum is always quarter. In conclusion, to conclude, dn is always quarter, and doesn't matter what n is. So dn is not tending to 0. And so the sequence Fn is not uniformly convergent. We can show it geometrically speaking, and yet again without any proportion or something like that. But what intuitively happens here? If you look at the x-axis and let this one be the y-axis, the points, oh, the limit function is 0. It's just the axis itself, okay? And the points where we get the maxima are getting bigger and bigger. Yeah, the square root of half, the third root of half, the fourth root of half are getting closer and closer to 1. These are the points. And the function are getting their maxima, which is a quarter, in this point. So the first function is something like that. And the second function is something like that. It gets the maximum in a different point, but still, it starts from 0 and goes to 0. In 0 and 1, both of the values are 0. And the third function, it should be, of course, above the axis. Let's do it more precisely, as far as I can. Let's say something like that. And then something with a different point of maxima, but same quarter, about the height, and from 0 to 0. And let's say in blue one, some other function, it gets its maximum even longer, and then etc. etc. These are how the functions look. And our, again, our limit function is 0. So just like the first geometric example, if you take the limit function and cover it with an epsilon stripe, let's say epsilon is 1 above 10. Remember that this height is a quarter. Yeah. So if you take an epsilon strip of, let's write down 0.1, all the function just burst out from our strip just to get to their maximum value of quarter. They get back to strip, but it doesn't matter. When you get out, the convergence is not a uniform convergence. Let's copy and paste that and give you some time to ask questions. Oh, it could be 8. It's always great. Okay, any questions about the process we just went through? The graphs we brought after?
So the definition of uh, the convergence, the more strong convergence,
Yeah, uniform.
depends on the weaker convergence.
Oh, yes, I defined it that way. I mean, we already need to know who is f,
To
the
have
function that limit function that fn point1 is converging to it, in order to decide if there is a uniform convergence. But as I mentioned earlier, we can define the uniform convergence using the phrasing of Cauchy with Fn and Fm smaller than epsilon
yeah, but
when you do not mention F explicitly.
you don't
And still
mention
the
it
same.
explicitly, but it has to be exist, right? If it's not point-one
Yes,
convergence, it's not the
of course. Yeah. If it's not point one convergence, it is not uniform convergence. So by my definition, it's clearly you need F to define the uniform convergence. Um, any more questions? Okay. So, I want to prove our theorem that this dn goes to 0 actually equivalent to all the stuff with epsilon. That's we defined the uniform convergence. So let's write it down. Proof of the theorem. We need to show two things. When dn goes to 0, then the definition of uniform convergence uh, happen, exist, suffice, whatever, and vice versa. So let's move on and write down explicitly what does uniform convergence means. Is it? So on one direction or in one direction of the proof, we know that for every epsilon, blah, 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 definition of uniform convergent. And we want to show that dn goes to 0 when or where dn is the supremum of blah, blah, blah. Let's copy it for somewhere. Now, the difference between dn, which is supremum, and the difference itself, fnx and fx, is very small. Yeah, I mean, what is supremum? We know that the supremum, that's how you write it, I think, supremum is the smallest upper bound. It is smaller than any other upper bound. Every upper bound, let's write it down that way, every upper bound is greater or equal than the sup. Now, by our definition, we want to show that dn goes to 0 by definition, and I want to use the definition of limit that we mentioned earlier to prove that dn goes to 0, because what is given to me, the uniform convergence, is phrased with this epsilon and epsilon stuff. So by definition, let sunshine, let epsilon greater than 0. Semicolon. We need to show that there is some an epsilon without the such that for every n which is greater than an epsilon, we have dn minus 0 smaller than epsilon. This is the definition of the limit. Now dn is always positive, and minus 0 we don't have to write down. So it's enough to show that, because, no, yes, because dn is always non-negative. What is this one? Where did you get it from? It's weird. Because dn is greater than 0, dn minus 0 with absolute value is equivalent to its if and only if dn is smaller than epsilon. And yet again, what is dn? It is the supremum of f and x minus fx. Now, by what is given to us right here, we know that f and x minus fx is smaller than epsilon. And dn is the supremum. It's the smallest upper bound. Every upper bound is greater than the supremum. And epsilon here is an upper bound of f and x minus fx. So intuitively, we've already got what we want. Epsilon, it is given to us right here. It is an upper bound of f and x minus fx. And as an upper bound, it is also greater than the sup, because the sup is the smallest one. What is the only technical problem? If epsilon is f and x minus fx, it is greater or equal the sup. It can be the sup itself. And formally, we want epsilon to be greater than dn. We probably know, I don't know if it was mentioned specifically, probably not the lecture in FE1, but in the homework or in the practice, that if we change the epsilon greater than the expression to epsilon is greater or equal than the expression, it's the same. We get the same definition of limit, they are equivalent. But on the other hand, if we technically want to uh, get our definition exactly as it is, we need to do some trick, not unfamiliar one. So by what is given to us, it is correct for every epsilon. There is an epsilon such that for every and for every, I don't need this R here. No, let me this T here. There is, let's get back where we copied it from. Probably the typo is there as well. Yeah. Another the pros and cons, another pro is that when you copy and paste, you do some debugging. You look at your own text, oh, right, this here over there. So for every n, for every x, we have the difference between f and x and fx smaller than half of epsilon. Now, why are you like this? Why are you the way you are? Okay. Yet again, here the every is on our side. It's a playable character for us. We can use this for everything you want, so we use half epsilon as always. Now, dn is the sup, and so it is smaller or equal to every upper bound. I consider epsilon above 2 to be the upper bound right now. So it gives us the sup less or equal epsilon above 2. And epsilon above 2 is, of course, smaller than epsilon. So we do get that dn is smaller than epsilon. As required. Now, in the second direction, knowing that dn goes to 0 and proving that the sequence is uniformly convergent is very similar to this one, but we'll write it down nonetheless. Any questions about our first direction? So,
Yeah.
on the other hand, yeah. You got a question, Sammy?
Yeah, can you hear me?
I hear you.
I thought we were showing that dn tends to 0.
Yeah.
How did we show that dn tends to 0?
By the wait a second, let's stop
Oh,
here.
because it's for every epsilon, which
Yeah,
means that it can only be 0.
yeah,
Oh,
exactly.
okay.
The very definition of a limit. So in the second, in the opposite direction, we have dn goes to 0, and we want to show that for every blah blah blah. Okay, so again, by definition, or let epsilon be some positive number. By definition, definition of limit, definition. By definition, I missed the E, right? Definition, the I. By definition, there is an epsilon such that for every n that is greater than n epsilon, we have dn minus 0 smaller than epsilon. Here we know that dn goes to 0, so this is what is known to us. Now, as we mentioned, it is equivalent to dn is smaller than epsilon, which is supremum of the difference is smaller than epsilon. Now, supremum is the smallest upper bound, but it is an upper bound. So it is greater for than f and x minus fx for every x. By the definition of supremum, we have that this one is greater or equal difference without the supremum, which means that f n x minus fx is smaller than epsilon. And this is true for every x, because the supremum, and for every n greater than epsilon, as we already stated, by definition of limit. And if it is true for every x in the segment, for every n greater than epsilon, then by definition, the sequence is uniformly convergent, as required. The n goes to 0 if and only if the sequence is uniformly convergent. Any questions about the direction? So, as I mentioned in the last part of this lecture, I want to re-ask the questions we asked on Sunday, but now we are given that Fn is uniformly convergent to F and not just pointwise convergent. Let Fn be a sequence of functions in some segment I uniformly convergent to a limit function f. As we mentioned, we can denote it with two arrows. First question. Fn are all continuous. Is f necessarily continuous? Now, the answer when we were given pointwise convergence was no. Now it is yes. We will not prove it today. What do you say to the God of proofs? Not today, but maybe that's what I want to do. That's the schedule. We will prove it in lecture number 14. It's it's Sunday, this Sunday. What I want to say here that first of all, it is not going both ways. I mean, let's write it down. Note. Second. Note. If f and f are all continuous, it does not mean that fn converges to f uniformly. the S here. It's like, oh, why are you like this? Uh, okay. For example, we saw that Fn is x to the power of n minus x to the power of 2n. F is 0 in the segment between 0 and 1. Both. It's infinite number of functions. Yeah, all of them. All the Fn on one hand and f on the other hand are continuous, but it is not a uniform convergence. What more? What is true, the equivalent um, theorem or claim or whatever, if Fn, on the other hand, we can say that if Fn are all continuous and F is not continuous, then necessarily Fn isn't uniformly converges. That is the correct way to look at the negative phrasing of this sentence. So, for example, in the segment 0 to 1, the sequence x to the power of n of continuous functions converges to the non-continuous function, which is 0 and 0 and 1 and 1. I'll write it down at the beginning of the lectures. Copy it from there. So Fn here isn't uniformly convergent to F because they are all continuous, but F is not. So this is our first question. Why the main answer is true? Why if the continuous is continuous? As I said, we will probably prove it on Sunday. Not promising anything, of course. So this is the first question. Okay. What about the second question about differentiability? If Fn and F are differentiable, is the series of derivatives converges to the derivative of the limit function. And I'm talking about even a piecewise convergence. One can ask it about a uniform convergence as well, but it doesn't have to because the answer is still no. Even if we have uniform convergence, it is not enough. For example, the functions we have seen earlier, this sinusine. This function converges to f, which is 0 uniformly, as we've already seen. We saw early in the morning, that Fn is uniformly convergent to F, but F and tag, and yet again, when I derive when I differentiate the variable is x. So if we look at f, let's put it sequence. The 7n goes out as the inner derivative. Sinus become cosinus above 3n. And after the n cancel each other, we are left with some constant multiplied by cosinus. It is not convergent to f tag. It is not convergent. That's it. Cosinus doesn't go to anywhere. For x equals 0, okay, not convergent. Of course, not in all of R. It is not convergent. F tag, which is 0. So yet again, even though we have uniform convergence, still we cannot say anything about the derivative. What can we say about the derivative? And I don't want to prove it today, maybe next week, maybe just you trust me, bro. But we'll use it when we come to serious functions, so it's important to write it, I think. What can I say about the derivatives? The following. Following, if the sequence, if I'm going from, we can get something from the derivatives about the original functions and not what we try to do here, getting something about derivatives from the original. So if the sequence fn is convergent for some point, even one point is enough. We know that it's convergent some point in I, and the sequence of derivatives fn tag is uniformly convergent to some function g in I by our notation, it is fn, right arrow to g. If we know that if we already know that the sequence of derivatives is uniformly convergent, then we can move backward and say that there is a differentiable function. Yeah, how are you? Function f such that fn converges to f, and it's not just a function, the derivative of f is this function g. So going backward here. If I know that fn tag converges to some function, then you know what? Fn also converges, and converges to who? The antiderivative of the function you know about fn tag. It's practically the same as the theorem about integrals, which we will not talk about today because we're already almost finished, but we will mention it and maybe prove it on Sunday. On Sunday about integrals, just say it without writing it down. The answer is yes. If fn converges uniformly to f, then the integrals of fn converges to the integral of f, which was not true Sunday when we already talked about pointwise with a nice example of rectangles or something. Okay. Okay, we are finished. By all means, any questions, Sammy, before we close the Zoom?
Yeah, I had
Yeah,
in the previous in point one, just if you scroll up a page.
yeah.
So we said if all of Fn continuous, then F is continuous. Yeah.
No, I can't hear you.
Can you hear me better now?
Yeah.
Okay. So we said if Fn are all continuous, then F is continuous.
No, it's again, can't hear you well.
Uh, can I type it?
You can try, yeah. Look at
Okay.
the
I pay for. I think I'm going. My brain is like a full and I need to go like groceries. Fair enough. So hopefully I see this logo and there. Just a reminder I'll be able to.
We say that if n is constant, f is const. If we know that fn, if we know that fn converges uniformly to f, then if fn are all continuous, you can conclude that f is continuous as well. Bye. But only if you, at first, you know that there is a uniform convergence. Okay? I need a confirmation to leave class. You don't have any other question. Yeah. No, not answer him. Yes, because xn are you are continuous, but the limit function is not, then it's necessarily not uniformly converging. Yeah.
Okay, cool. Thank you.
Yeah, bye.